Hello, everyone. Welcome back to class. This is Dr. Dax. We are in week 5 and we are looking at our first class of the week. And we are in the QMB5000 class, and we are going to be looking today at regression and inference. Two very important topics in the field of data science because they deal with the area of predictive analytics and help us to make decisions based upon historic data and predictions about the future. Ideas that are at the very core of what we design our machine learning algorithms for, and it's kind of what we're all about. And so I'm really excited about that. Before we get started, I want to thank you for tuning in, for watching this recording. We could not record on time yesterday due to unforeseen circumstances, and I appreciate you being flexible and working with me in this. For the remainder of the term, what we'll probably do is end up recording a lot of these and just posting them as they come up, and we'll do at least 2 a week. So any questions as we go along, please shoot me a message, let me know, and we will get you going. All right, so without further ado, let's go ahead and take a look at our objectives for today. I want to get diving right in. So today we're going to be defining inference, and I want to look at the 3 forms of inference, what that means in terms of data science, and we will explore the square root law. I want to explain the null hypothesis and clear up any confusion that we've got in that area. I want to cover the fundamentals of regression analysis, and so my goals are pretty simple. I want you to walk away with a familiarity of inference and regression, and we'll be able to see an example of that and be able to explain the confidence interval, and you'll understand that there is a difference between confidence interval and probability. All right, so let's go ahead and take a look at what we've got going on. Time permitting, we will perform an objective analysis on a data set that I've put together from several different sources, and we'll explain all that as we come to it. All right, so inference. Sorry, it's not working. Okay. Statistical inference is the act of generalizing from a sample to a population with some calculated degree of certainty. What we've got is a large population. You've got a parameter of, let's say, a large data set. And what we do is basically we want to learn about the population parameters, but we can only calculate sample statistics. So the reason we're doing that is probably because it's not feasible to look at the whole population, maybe due to the size of the population, due to resources or what have you. We'll talk about that. What we're interested in, if we're taking a sample, is precision and reliability. They're not the same thing. Let's talk about that. How precisely does a given sample mean, which we're going to refer to as X bar, reflect underlying population mean, or mu? And how reliable are our inferences? So let's answer those questions by considering a simulation experiment in which we can take all the possible samples of size n taken from the population. So to answer the question, what we're going to do is establish the concept of a sampling distribution of a mean, abbreviated SDM. What we have is a population, which we'll show you in the next slide. It's going to be in the first figure. And the n, which is your sample size, a logarithmic shape, the mu, which you'll remember as the population mean, and sigma, which is 30, and we'll explain that in just a second. And we'll take repeated SRSs, each one of n equals 10, calculate the X bar in each sample, and plot the x-bars, and that'll be in the second figure. Because of the concept of the SDM, it's necessarily abstract. What we need to do is employ simulation experiments and try to embody the concept in this way. The simulation experiment is based on a population of adult males with a mean body weight of 173 pounds. Let's take a look. The distribution has a positive skew and a standard deviation of 30 pounds. So the experiment will basically proceed by taking many independent SRSs from the population. And each sample has an N of 10. And we calculate the mean from each sample, study the distribution of the sample means, and the table will show the first 5 independent SRSs from the experiment. It should be in your ebook, and the mean and standard deviation of each sample varies. After several thousand repetitions, we can plot the means of the independent samples. The distribution of the sample means is shown here, and this represents your SDM. Let's take a look at some of the findings from the experiment. First of all, what we know is that the distribution B is more normal than distribution A. That is the central limit theorem. Secondly, we understand that from this experiment, both distributions centered on mu x bar is unbiased estimator of mu, the sample mean. Third, distribution B is way skinnier than distribution A, and that is due to the relationship of the square root law. So finding 1, basically, let's reiterate it. Let's go here. Basically, finding 1 is that the SDM looks like normal, even though the population is not normal, because of the central limit theorem. Note that this will allow you to use normal probability calculations when making inferences about the population means. Finding 2 is referred that although some sample means will be less than the population mean and some will be more, these differences will balance out in the long run. Thus, sample means provide a fair or unbiased reflection of the sample mean, or the population mean, sorry. And the third finding is that the SDM clusters more tightly around mu than individual observations. In other words, sample means are less variable than individual observations. The findings also suggest that a good measure of the precision of the sample mean is the standard deviation of the SDM. The standard deviation has a special name. It's called the standard error of the mean, or SE. And we refer to that as sigma, the funny looking O with the little line over it. So whenever we refer to the SE, the standard error of the mean, you'll see it expressed like that mathematically with that sigma symbol. All right, let's take a look at what we mentioned a minute ago, the square root law. Oops, sorry. First, we got to see the standard deviation of the mean. We've got the standard deviation of the sampling. Distribution of the mean has a special name. And remember what the square root law says. All right, let's take a look at the square root law. Basically, we are looking at the Welcher Adult Intelligence Scores. Basically, this has a variable with a standard deviation of 15. This slide shows a calculation where the SEs for the variable when n equals 1, the standard deviation winds up being 15. But we can see what happens when we change the value of n. Let's change it to another sample size. Let's say if n equals 4, what do you think will happen to the standard error? Will it go up or will it go down? It actually reduces. So the larger the sample size, the smaller the standard error. Now let's go to 16. It gets even smaller. So what we're learning here is that the precision of the sample mean is inversely proportional to the square root of the sample size. We know this because in this example, the mean based on a sample of n equals 16 is twice as precise as a sample mean of n equals 4. And we've proven an inverse proportionality. Now, while we're talking about inference, think about what inference means. Inference is, from a literal standpoint, it's when you make a judgment about anything based on previous history. We know A, B, and C from our previous experience, so we can infer that D must be true because of our knowledge of historic events of some kind. In data science, it works exactly the same way. We're inferring from previous information and taking that sample and building a predictive analytic model on what we think will happen with a certain amount of probability given what we already know. But inference takes different forms. One is hypothesis testing. And we'll talk about what that means in just a second. Related to that, it's confidence interval estimation and point estimation. So in hypothesis testing, let's take a look at that for just a second. That assumes that we've got our sample distribution plotted out. And what we do is we've got in this drawing here a bell curve. All of the events and elements of the sample population are plotted out in what we call normal distribution. And here on the right, you see H sub A is more probable because it's farther to the right in the right tail test. Left tail test, H sub A, mu is less than the value. H sub A is more probable. Using hypothesis testing, what we're trying to do is interpret or draw conclusions about a population using sample data. A hypothesis test evaluates two mutually exclusive statements about a population to determine which statement best supports the sample data. And it can be charted out in a confusion matrix like this. And that's where we get into type 1 and type 2 errors. So basically, when you formulate a hypothesis, what we're interested in is determining whether or not a null hypothesis is false. And if it is, what we do is we can mark this side of the confusion matrix and determine whether or not we reject the null hypothesis. So if the null hypothesis is false and we reject the null hypothesis, what we learn is that the outcome is true and correct. So let's take a look at an example to kind of clear up the muddy waters, because sometimes when we're talking about forming a hypothesis and in terms of data science, it gets a little bit muddy, a little bit confusing, because we use these weird terms: rejection of null hypothesis. Why can't we just say, I have an idea what might happen, and this is it? Well, let's take a look. In this example, let's say you want to rent an apartment and you have a budget of $550 a month. So what you can do is you can gather a sample of apartments with a range of a budget from $350 to $1,200 a month. Now this budget has to include everything, not just the rent, but the utilities as well. So you select at random some sample of apartments and assume the hypothesis. Now this is where the terminology comes in, so hang on to this, okay? We're going to say H sub 0, hypothesis 0, you will rent an apartment. H sub 1, you will not rent the apartment. There are only two possible outcomes. It is a binary situation in a null hypothesis. So since you will not rent anything above $550 a month, this is what we call the critical region. If the apartments fall within the critical region of some number above 550, you will reject the null hypothesis. And I hope that makes a little bit more sense. Let's put some visual to it. In this spreadsheet, we've got these fictional apartments set up. There's the price, and you can see the utilities that are averaged out, the total here, and the choice numbers. And what we can do is we can highlight all of them and plot them out. And through the magic of editing, we're going to go ahead and do that. So let's say we've plotted them out. Now on the Y value, you can see the dollar value of the total. On the right is the choice number. And so remember our cutoff point in the critical region. What was the budget? It was 550. So right in this region here, a little bit less than halfway up, is the cutoff point for the critical region. Watch what happens. Now everything above that is your critical region. That becomes the area in which every apartment that falls in within that is where you reject the null hypothesis. And another measure of inference is the alpha, which we refer to as a level of significance. So let's take a look at that real quick. And the level of significance, basically the significance level is, in simple terms, the threshold probability of incorrectly rejecting the null hypothesis when it is in fact true. It is basically the probability of a type 1 error. It's also the size of the critical region. Basically, strong control of alpha is desired, and in tests, it is prefixed at a very low interval, like a small percent. If H sub O is not rejected at a significance level of 5%, then one can say that our true null hypothesis has a 95% assurance. So your significance level is, well, it's significant, but it's not the same as confidence interval. So basically, so far we've described choosing an outcome that is essentially one or the other. It's either considered good or it's considered bad. But there is a range of possible outcomes or plausible values for an unknown parameter, and that range will have an associated confidence interval. Let's take a look at what that means visually. So the confidence interval is a range of values that's likely to include a population value with a certain degree of confidence. It's often expressed in terms of a percent, where a population mean lies between an upper interval and a lower interval. Now you can see here in this expression that 95% of your population mean falls within this upper bound here and this lower bound here. And so this is your 95th percentile. Outliers are on each end of the tails. 2.5% on this end, 2.5% on this end, and the mean is right here. Basically, the 95% confidence interval is a range of values that you can be 95% certain contains the true mean of the population. As the sample size increases, the range of interval values will narrow, meaning that you know that mean with much more accuracy compared to working with a smaller sample. And you can visualize this using normal distribution. And whenever you see a bell curve plotted out like this is what we refer to as normal distribution. Okay? So, for example, the probability of population mean being between negative 1.96 and positive 1.96 standard deviations, or z-score, from the sample mean is, you might have guessed, 95%. Another way to say the same thing is there's a 5% chance that the population mean lies outside the upper and lower confidence interval. So then the magic question becomes, why even use confidence intervals? Basically, we take a sample of a population because it is not feasible, it is not plausible to study every single person in a population, particularly in a large study. So researchers take a sample or a subgroup of the population, and confidence intervals with a high degree of probability and a high degree of confidence are desired. Basically, the researcher can only estimate a portion of the parameters, and not a portion of the parameter, a portion of the population, and they can get a look at the parameters and chart them out, and the estimated range being calculated from a given set of sample data, and they can extrapolate that on the whole population. So the confidence interval is basically a way to measure how well your sample represents the whole population you're studying. So what we're saying is there's a lot of assumption going on, and that is why the confidence interval is important. So some things to remember. We're only able to observe the parameters in the previous examples of a sample population. It is not likely to build complex evidence of correlation without further investigation. So inference can be tricky if you don't have enough information. The larger the sample size, the higher the confidence level, the more accuracy you have, but it's not always enough. So for that, it helps to have a tool like regression analysis. Now, what we do a lot of times in data science is regression. And basically, what we're interested in with regression is we're taking the ability to use historic data and infer a relationship between variables, usually two variables, like an example like this. And they're saying y and p in this sample here. And what that does is it allows us to create a situation where if we know one bit of information, we can infer the other bit of information based on the trend. Now, in this example here, you have a positive skew, meaning that it skews up to the right. If it trends down to the right, that's a negative skew, but there's still a relationship. Recall that much of what we do is we try to study elements that imply causality. And what I want to do now is I want to take this a step further. A lot of times in data science, we use our skills to chart statistics, to present statistics as evidence of causality. That's the backbone of statistics and data science. And so oftentimes we're called to present information about things that are considered sensitive topics, hot button topics. And so a recent idea that has come up is the minimum wage question. Now, I wanted to bring this out and plot this out, but before we dive into this, I wanted to just say that a lot of times what we do is pull in examples that are culturally significant, ideologically significant to a lot of people, and maybe sensitive to a lot of people. And I want to reiterate that in data science, our job is not to prove anyone right or prove anyone wrong, particularly with regard to ideologies, politics, and things like that. I leave all that stuff at the door. You must remain objective. You must remain logical and leave your passions at the door in this job. If you can't do that, it might be wise to consider alternative career path, because we're interested in being able to follow the numbers and follow the evidence and present them in a way that is true, logical, ethical, and correct. With that being said, there's evidence on both sides of just about every argument, and so I'm not interested in how you vote or how your politics lean. I have voted on both sides of the fence and all over the place. I've got friends that are all over the place in ideologies, and so I don't make any judgments. And in our classroom, we don't make any judgments, and we don't argue about anything. And this kind of example is not to promote any kind of argument. Our school is not about promoting any kind of ideology, left or right. We're just trying to train you on the technology and prepare you in a way that is fair to you, and in a way that you can present your knowledge to the world and create something positive for society as you go out. So what we're going to do is take a look at some historic data, and we're going to try to infer possible causality. And the question becomes hot button questions like, should the minimum wage be raised? And if so, would it be a good thing? And if so, would it be a bad thing? If it shouldn't be raised, why not? Would it have a negative impact on the economy? Well, those are all important questions, and they're multi-layered and complex, and we're not going to answer them all, but we can take a surface level look with the time that we're allotted. What I'm going to do is I'm going to show you a spreadsheet that I pulled up. Let me get that going, and I think it's going to be here. Hopefully you can see that. Let me get that going. All right, so anyway, we are looking at the spreadsheet now, and you can see at the top we got the year, fuel price, minimum wage, average unemployment. So the reason I did it this way is I was interested in knowing what has happened in the economy every time minimum wage has been raised, because the question of should we raise minimum wage should be something we can look at pretty easily by looking at history. So I've looked at some numbers based on fuel prices, because that tends to follow the economy. I've looked at unemployment rates, because one argument is that when minimum wage is raised, it leads to higher priced products and layoffs, and employment. And so there are lots of other elements we can put into it, many features, and a much more detailed study. But this is one that we just threw together for the purpose of analyzing the question and just kind of generating getting your juices flowing. And so I went back from 2019 to 1992, and this is all information from the Department of Labor and other places. That all the information is freely available on the internet. You can Google fuel prices, national average fuel prices per year, and just plot them in and what it looked like. And what we can do is plot them in Python pretty easily. So what I'm going to do now is go ahead and start that process. And it's just a few lines of code, because all we're really doing is I'm going to create a scatter plot. So let's go ahead and import pandas. And I'm going to use a data frame. pd.read CSV or R C. And I'm just going to go ahead and copy the path. Now, I'm going to pause right here and let you guys know, the other day when I was working with some of the assignments, I had to take the paths that you guys had put into your script and take the slashes that were forward or slashes that were backward and flip them forward. It was kind of a pain in the rear end, and I discovered a thing that I'd forgotten a while back. I'll share it with you now. And that is very simple. If you are copying your path in Python for a data set, you don't have to go through and iterate each little slash and flip it the other way as I was doing the hard way. There's a shortcut to that, and I just did it. Before you enter your path, before you do your quote and your path, just put an R and then the path. And that way, if you're using Windows, I don't know about Ubuntu and Linux and that kind of stuff, but in Windows, when you copy things, the path is always leaning left like a backslash. Python interprets that as a dividing slash, and it doesn't like it. It'll kick out an error unless you put an R in front of it. So yeah, in front of your path, R, boom. Problem solved. Look at that, no errors. Life is good. So what I've done is I'm going to create that. I've got the data frame there, and I think what I'll do is go ahead and plot out unemployment over the years. Let's see how that looks. Let's see, we got our minimum wage here. I'm going to go ahead and do a scatter df. Whoops, need to go again. df. I believe it's plot dot scatter, and we will set up y equals average unemployment, and I want to set the year up as the x value so that we see how, as the years go by, what unemployment looked like. So x equals year, and I'll set the color to red. I did not like that. What happened? Invalid syntax. df dot plot. Oh, I know what I did. I think it's because I did a single quote on one side and double on the other. Let's try it now. Okay. Let's see if I can get it to show up a little bit better here. So hopefully you can see that. So it looks like unemployment was around 7.5, and it went down until about 2000. Then it went up to about 6, and it started to go down over the years to about 2006, and it spiked up about 2010, and it went down to about 2019. So that's interesting. Hopefully you can see that. Let me go to the output, see what you're looking at. Okay. Now let me take a look at the minimum wage. Let's see how that turned out. Let's see. I want to go. I want to rename that as DF2. F2. And then we'll do a DF2 dot plot dot scatter y equals minimum wage x equals year, color equals blue. EQL while scanning string literal. Good with something else. Okay. I don't know what that means. EQL while scanning string literal. DF2. Plot dot scatter. Parentheses y equals wage x equals year equals, oops, missed my quote. Let's try that. Change this back to DF2. There we go. Now I want to go back to looking at your plots. Let's go. There it is. Okay, yeah. All right, so now we see in 96 minimum wage spiked, 2006 minimum wage spiked. That's very interesting. Wonder if we can plot them both together. Let's go back to Python and see if that's. I've forgotten how to plot them at the same time, but let's give that a try. I'm going to try to. So let's do DF2, y equals minimum wage. I wonder if I can add y sub 2. y2 equals average unemployment. It'll let me add 2 y values. No. Has no property y2. Okay. Well, anyway, I don't seem to be able to get both of them at the same time just right at the moment. So let's go ahead and go back to our plots. Now, with the minimum wage, we saw that at 96 there was a spike, and at 2006 there was a spike. So minimum wage was up at 96, 2006, and unemployment went down until 2000, went back up 2004 about, down to 2006. Spiked about 2006, 7. Same time minimum wage went up. So there's some evidence for causality between unemployment and minimum wage, but not actual proof. So what you can say is there is some evidence there. But just remember that in statistics, it can be tricky because if you play with the numbers and flip the values one way or the other, you can actually make the argument both ways. Let's take a look at the Excel sheet real quick and see what happens. Let's take a look at fuel prices. Copy that, and minimum wage, and plot that out. So there's a little bit of a parallel. So as minimum wage went up, fuel prices went up a little bit. A little bit of parallel. All right, let's take a look. Let's delete that. Take a look at minimum wage and unemployment together. Chart that out. Now it's a little bit more muddy, isn't it? A little harder to imply causality. Hopefully you can see that. Let me move this over a little bit. So it looks like as unemployment went down here, there was a spike in minimum wage at this point, but unemployment continued to go down. And minimum wage stayed the same, unemployment continued to rise. and then it went down again. Minimum wage was brought up incrementally, and minimum wage went up, and unemployment started to go up. But as minimum wage flattened out, unemployment began to drop right around here and continued a steady decline. So with some tweaking, you can make the argument one way or the other. It's really a dangerous territory to get into, depending on whether you want to present the news one way or the other. Keep that in mind whenever you are watching anything and the news is presented from one source or the other. Look at the numbers yourself. I encourage everyone to run the analysis, find the data source, question all the sources, and follow the numbers. I encourage everyone to think independently and follow the numbers yourself, and try to encourage others to do the same. So that's about it for now. I hope you enjoyed this talk on regression analysis and inference. We'll talk more about that in the future as we dig a little bit deeper. And if you have any questions about anything, shoot me a question at dax.bradley@rasmussen.edu, or send me a text at 252-458-7176. And I look forward to talking to you guys again. I'll pre-record a message and send it out on Thursday because the hours at work have been a little bit crazy lately. I do not know if I'll be able to do a 7 o'clock Thursday showing, so let's do a pre-recording, and I will get that posted for you on Thursday. And I look forward to it, and I hope you do too. We'll see you again soon, guys. Take care. Everybody be safe.